So we're going to continue with William Zhang, who will give us an overview of abstract harmonic analysis.
Yeah, I'm William Zhang, which is a freshman. So maybe I think I'm still not so skillful about the abstract harmonic analysis. So I just like to talk about two theorems. One of them is abstract algebra, and another is the other is harmonic analysis. Yeah, let me start. The first theorem is about the topological group. Yeah, I'd like to recall the definition about that. Here we have a group, G product. And if we give it to a topology tau, such that the two functions one is product and the other is the inverse, the two function is continuous, then we tell that this is topological group. How is we given topology on G? So then we can define two functions. One of them is LA, and A is we fix some point in G, which defined by send some point G to AG. This is a homeomorphism from G to itself, because if we separated it to two steps, this is a continuous functions because of this is a product topology. And the second step is also continuous because of that. So LA is continuous function. Also, it is bijective because we are not hard to find the inverse of that. It's just that. So it's a homeomorphism. And similarly, we can define RA, which is the right product.
Slight detail missing. It's a homeomorphism.
Yeah.
Because not because the inverse exists, but because the inverse is another map of the same kind, and therefore it's continuous by what you prove. So
yeah.
Therefore,
so,
of course you noticed that yourself, but you didn't say it. So I'm just
yeah.
Well, I don't know.
Yeah, fine. I know that.
Yeah.
Yeah. Okay. So
no, you didn't need to change what you wrote. What you wrote was correct. That the inverse of LA is the L of A inverse. But you forgot to say that you forgot to point out that L of A inverse was continuous.
Yeah, it's also continuous.
Yeah. Okay.
And we can buy. Yeah.
Okay, that's
fine. Thank you. Thank you to the remind. And there's two are homeomorphism from G to itself. Then we can define some things. So consider an open set, which is in G. Then we can define G inverse, which is the set of the inverse of all elements in U. If U is open, then U inverse is also open, because this is also a homeomorphism, right? And also, this one is also open if U is open, because it's equals to LAU. This is a homeomorphism. Moreover, if we take some arbitrary subset of G, just A, if U is open, this one is also open. Yeah, this is some preparation, and
well, you have to say what the preparation is.
Yeah.
What do you want to do now?
Yeah, I just want to show that all topological group is regular, right? And regular means the T3, which means just like the Hausdorff, the definition of Hausdorff, but we just changed one point to a closed set, and we can find two open sets to separate it.
Well, I don't think a topological group has to be house group, not unless you.
Yeah,
Not unless you say so.
maybe we have some some conditions. So just continues.
Calm down. By the way, what is the, maybe you can give an outline of what you want to say overall today. What is the main thing you want to say this afternoon?
To say that the topological, I think some of topological group is regular.
Well, yes, okay, but is that what you want to concentrate on? Is that the main statement?
Yeah, this is the main statement of one theorem I want to prove.
That's not 6 pages. I mean, you've got a whole lot of pages.
Okay.
What's the main thing?
Main theorem is just all. Yeah, it's just this the topological group is T3.
That's not true.
Maybe we should add some condition.
Look, if you say a T3 topological group is T3, that's true, but that's not interesting. You have to, if you want, your definition of topological group is very, very general. And if you want to have special properties, you have to assume it. You can't prove it.
So just begin our proof
But
of
what you want to
that.
do is give examples. If you want to give some interesting examples.
Pardon?
Well, I just want to know what you want to do. What you just said you cannot do. You can't do that.
Yeah.
So you can't. That's not true. It's not true that every topological group is T3. It's not true. It's not true. But what you want to do is give an example of a Hausdorff topological group.
A Hausdorff.
Yeah, why not give an example of a topological group? One topological group which is Hausdorff, and another one which is not Hausdorff. Can you give examples of that?
The Hausdorff group just
Okay, the real numbers with the usual column.
yeah with the Euro topology. So
R plus non-zero. Non-zero is non-zero.
yeah, non-zero is non-zero.
Good. That's Hausdorff. And what's an example of a non-Hausdorff topological group?
Sorry, let me think about it. So can I continue? Just finish the proof of this part. Maybe it's just a part of
what?
of some of topological group is T3, and I finished some proof. So
What's T3?
Regular. So
What's the definition of T3?
it's like that.
Yes, but I forgot. I didn't quite follow what you said. Basically, you're saying if you have a single point.
Yeah.
And
a closed set.
And a compact set is different, this way from it.
Yeah.
Then they're separated by disjoint open sets.
Yeah. Closed set.
These are the circles that are.
The circle is open. Are open set.
When I draw a circle, that's what I said. It's open. The circles are open sets.
Yeah.
That's what I said.
Well, T3 separates point and the closed set, not a compact set.
Oh, the square is a closed set.
Yeah. So that's
when a closed set.
that means T3 or regular.
They're separated by.
Yeah.
All right, but of course.
Yeah. So
can I just point out though that T3 is regular plus Hausdorff. So regularity for topological spaces is a different condition.
Sorry, who is speaking?
Yeah, I mean, my name is Abhijit, but I'm an international student. I'm just attending these seminars.
All right, good. But you might introduce yourself to one point. But anyway,
I'm sorry, I barely hear you, so I cannot.
Same sort of observation after there. So I think usually T3 means your T0 or sorry, T1 and regular. So regular in the sense that you can separate points.
Yeah,
Close
and a
set
closed
from
set.
But T3 usually also means that points themselves are closed sets. So you usually measure one point. But I don't know if you're assuming that in the definition of topological group, because as George mentions, not all topological groups are Hausdorff. So if you were T3 in the sense that I said, you would be Hausdorff.
Yeah.
But you can have regular spaces where points aren't closed. And so they would be regular but not Hausdorff.
Yeah.
So which version are you proving? Are you proving that?
Yeah. Right. Just that.
I'm surprised if there's something from the way you define topological group. So the topological group, I'd be surprised if there's any single property that is not mentioned, which always holds. Because points are not always closed. It's not always closed.
Yeah.
I doubt if it's always regular. But whatever the definition of regular is.
So maybe we cannot assume that the single point is closed. It's
If you assume a point is closed, then you will have every such topological group is different.
If points are closed, then this property does hold.
Yes.
Yeah. Okay. If the points in the closed set can be separated by open set.
the last row is we can take all A in A, then it's just the union of this open set, so it's also open. And also we define that the symmetric open set just means that U is equals to U inverse, and we not hard to prove that we can find the neighborhood basis of E from this symmetric open set. Just because we can find the symmetric, which is U intersection U inverse, which is in U for each open set, right? So this is also a lemma. So let me start.
What do you prove?
So
What is T3 remind you?
the single point and the closed set can be the single point is not in the closed set, which can be separated by two disjoint open sets. Yeah.
Well,
Let me prove that.
Are you assuming the points are closed? Yeah. Well, this is not.
I already assume that. So
Assume what?
assume the single point is closed. So maybe I should.
That's not the usual. That's not the part of the usual definition of topological group. So we have to put that down. You put that in the hypothesis.
Yeah, hypothesis is
That's T1. If the points are closed, that's T1. So you're saying that if you have a topological group, then T1 implies T3. Is that what you're saying?
right. Or T1 topological group.
Okay, good.
Yeah. Then let me prove that. Suppose that A in G is closed. There's some single point X in G, and X is not in A. Then we have what? Yeah, of course we have X is in A complement, and A complement is open in G. Right. And because our product function is continuous, so we can take the pre-image of A complement, which is just this notation, which means the pre-image preimage of AC with the product function. So this one is also open. It's open in G square, right? And since
Sorry, I've lost track. What is that point? What is that point?
sorry, the point just means fxy. If xy is x times y, this means it's same with the f inverse.
What's the function of two variables? I'm not sure what. Oh, is it equal to G squared to?
Yeah.
Sure. So that's true.
Okay. So since x times E is equals to x, which is in AC. So we have XE is in the preimage. So we can say what? We can see this set is a neighborhood of XE. Just because this.
Because X belongs to.
Yeah, X belongs to AC, and yeah, that's okay. So by the definition of product topology, we can find two basis neighborhood. V of X and W of E. And we require that W is symmetric. We already explained it because we can find the basis neighborhood just from the symmetric. Such that XE belongs to V cross W, and which is in. Yeah, this is called the basis criterion. And by definition of product topology. So we can say that. That's right. So we already find the neighborhood of X. Then we should find the open set of this. So how to find that? We take U is equals to AW. The definition just like this. So first, E is in W. So we must have A is in U. Right, because E is in Z. And also, because we already proved that if U is open, then for any subset A, AU is also open. Yeah, I mean, U is open. It's an open set, which include the A.
Is W just going from, if U just going from V?
Yeah. Next, we should prove that. Yeah. Assume that. Assume that there exists some G, which is in U intersect V. Yeah, since G is in U, which is AW, right? Which is AW. We can find some A in A and W in W, such that G is equals to AW. That's right. Yeah, and now we times the W inverse right. We can get A is equals to G W inverse. That's right. And we observe G and W inverse. G is not only in U, but also in V. And since we require that the W is symmetric, so the W inverse is in W inverse, which is equals to W. So we can see GW belongs to V cross W. Because yeah. So GW inverse belongs to V times W, right?
Well,
so we can get what? Yeah. That's right. A is equals to G W, which is in A complement, because we already have that.
In a complement.
Yeah, A complement.
No, not complement, it's complement.
Yeah, complement. Sorry.
Good.
Yeah, my English so poor.
No.
Yeah. So that's, I think that's yeah, that's already contradiction. So we have what? We have
Well, A belongs to A, but on the other hand, this belongs to.
Yeah. So we must have this intersection.
Okay, well, this.
It's empty.
Okay, good. But, you know, I'd like to see your proof, like, to understand, you know, a little better. Does anyone understand this proof? I mean, I suppose, I followed this proof, I followed every step. Okay, I'm convinced it's correct, but, and maybe I could even, go through it myself, just sort of go step by step. But maybe I couldn't, maybe I get lost, I wanted to draw some picture. So, did you invent this proof yourself, or did you look it up? Doesn't matter.
Something by myself, and something I look some material.
What did you look? You look partly you look.
Yeah.
Where did you look at the
I look just about take this and take this. I when I saw that W is symmetric, then I understand what we should do. Because I'm not so skillful about the symmetric, and when I say that I check the definition of symmetric. Yeah, then I complete the process. I think this step is too hard to think, but if we already have that, this is not so hard.
No, okay, well, I would say that this is a good demonstration. But I guess that's it for today. If you want to give me some more written things, then that's I don't think you've given me your final written report. You sent me an email about it today, but I don't think you included a revenue report yet.
I think this is
No, you did. Oh, you did. I'm sorry. You did. You have a summary. You have a summary of is that already your final report? Five parts.
Because I just have time. I think not five. Actually, it's 3 parts. And because I separate the preparation and the proof as 2 parts. Right.
I haven't looked at it closely. So that's very good.
And
One more. I don't prove anything more now. But you want to state was there one more thing you wanted to state? Was there one more statement you wanted to make? Anything more? So this is already your main theorem. This is your main theorem. You said that this was the main thing you wanted to do. Let's just leave it with that.
and I have another another theorem about the harmonic analysis, but not abstract. Yeah. Okay. We define f hat gamma like.
Okay, good. Just really important for function building your life. Good.
Yeah, and we have a formula set the Poisson formula, which is the and I learned that we can use this to do a lot of things because yeah, we can guess the if so we take the sum of this is hard, but we can easily to take the sum of this. And about the computation of this, I like to say about that by a few sentences.
Applying function.
Yeah. This is behind this step. We should first prove that. Yeah, I think it's not so hard if we use some complex analysis. So this have 2 parts, cosine part and sine part. And the sine part, since this is an even function, and an even function times the odd function is equals to an odd function. So we can just consider when gamma is positive. Then we will get the same result. First, we consider that if gamma is 0, then I think it's not the hard integral, it's just the arctan. So we can get pi over a when gamma is 0. And if gamma is not 0, then absolute gamma is positive. Sorry. Yeah, that's right. Then we can just let HC is equals to C squared plus A squared and e to the 2 pi I gamma C. And we integrate on that. we can integrate on that. And the singularity about these functions is minus IA. Yeah, we may suppose that A is positive and positive IA. So in this, we just consider about the positive IA. Then we use the Cauchy integral formula. This part plus the half circle is equals to 2 pi I. And this will rewrite this to say plus IA, say minus IA. So we just take the IA in this part, which is 2IA e to the 2 pi I gamma times IA, which is pi over A e to the minus 2 pi gamma A. And if we take the R goes to infinity, the integral on the half circle will goes to 0. Because we have a lemma, we can take the limit of the z goes to infinity, z times hc. And if we have some point and very little circle, we can also use that, just z equals goes to 0. And we times I and this angle theta. Then we can get the limit of the integral. So obviously, if we times z on these functions, when z mod is goes to infinity, the integral on it goes to 0. So we can get the integral on R is just equals to that. Then we got the answer. And these two can be combined. So we can just take the summation of this, and it's just the easy thing. So we can take the sum, and finally we got the result, which is yeah, and use the formula, we can get the result. It's equals to, yeah, we take n. It's not hard to compute. Pi over A and 1 plus e to the minus 2. Yeah. Okay. So just use this. So the summation of this on whole z is just equals to this. Yeah, that's all.
Okay, well,